at the beginning of the last class, when I went into Zoom, there was a research meeting going on in my Zoom room before, and I got off so I could prepare for class, and they were still going. So, and it was a research meeting with people from Japan, so it was about 8 in the morning over there. And so people started getting on and like, what's going on? Where's Brother Corey? So I had to kick him off. So, yeah. I've been researching Japanese math teachers for a while, but I don't speak Japanese. But I have a colleague that speaks Japanese, and I have a Japanese colleague that speaks really good English, so I have to trust in them. So, but they are really good math teachers. All right, let's get started. Any volunteers to offer a prayer for us? Go ahead, thank you. And it's Haley. Thanks, Haley. Amen. Thank you. Okay. Any comments about devotional from yesterday with Bishop Budge? Anyone remember what he talked about? Anyone watch devotional? Anyone? Anyone? Bueller? Bueller?
I mean, I know they talked about horses and about how if we have to yield ourselves to God by being willing to be vulnerable to Him. That's what humility is.
Yeah, great. Yeah, he used a great example of talking about what horses do when they begin to train horses and why they do it, and made an analogy to what God asks us to do, to break our heart, not a broken heart, but a broke heart. A broke horse is one that will submit to the master's will. So there's the great quote by Neal A. Maxwell that says, our will is really the only thing that we have to give to God, because everything else is His already. Right? Well, the only thing that we have to give, we have to sacrifice, is our will. So, yeah, if you didn't watch it, strongly encourage you to go to watch it. It was really good. Any comments about the essay that I had you guys read last week? The When Will I Ever Use This essay? Go ahead, Colin. Okay. Yeah. Okay, thanks. Hey, someone else. You guys can fight it out. I don't know who was first.
I thought it was really, really cool. And it doesn't even like just apply to math. It could be just learning in general. When someone takes like a general ed biology class at BYU, they're like, when am I ever going to use this? But you never know when you're going to need that information.
That's right. Yeah, I've got emails from people that have found it online. One was like a biology teacher, a physical therapy teacher back east, and she's like, I've been looking for an essay like this for so long. This is perfect. So yeah, it just doesn't apply to math. Okay, go ahead.
I really like your example when you used the quote right? If we know something, right? If we don't know, we will never know when we could have used it. But if we do know it, then we can just use it any time in our life.
Yeah. The original version so the original version was written for you guys, and I didn't use a quote. I used a scripture. And there was actually a whole nother section. I'll post it and have you guys read it. There was a whole nother section about learning in the gospel light, and I had all these quotes from like Brigham Young and stuff, and Joseph Smith about knowledge and how important it is. That got cut when I submitted it to the math magazine that it got published at. But yeah, the scripture I think is a more powerful example for our context, that when you know those scriptures and those principles, it'll come to you if you know it. But you don't think of, oh, can I go look up a scripture right now that might help me out? Seth.
Yeah, I thought it was funny, like when you did, like you quoted the teacher S.W. Kimball.
Yeah, I should have been a little more brave and should have put the religious leader or something like that, but I done Spencer W. Kimball. But, oh well. Okay. There's another reading this week. It's actually for your homework today. The 2.3b, there's a book we're going to read quite a bit of. It's a really easy book. It's a really kind of soft introduction to the way matrices are used. It doesn't always go into the why they do things, but it does talk about how they're used a lot, which is something that we don't always get to go into in this class very deep. So it's a book you all have access for free online through the library. The link is already in if you go to Learning Suite and you go to the assignment, the link is already there. This assignment is to read the first 2 chapters. The first chapter is like 4 pages and the next one's 8, and it's small pages, big type, and plenty of pictures. So it's like not that hard. These first ones are going to seem really familiar and maybe not have lots of new things, but he has some really nice examples of using matrices that we'll be getting at later. And the assignment part is to read it, and then you just write up a paragraph and state in the paragraph that you read the whole thing, so we can give you full credit. And then just a couple lines about the response, about things you learned or things you thought were interesting. Okay. Any questions on that? So I'm dropping off some of the proofs from some of these homeworks, so to counteract the time that you're doing reading. So in the other classes, they have another proof or 2 each week that they're doing, and instead you guys are doing these readings. So I'm hoping it kind of balances out. You guys would rather read anyway. Okay. Okay, before we go to the problems of the day, someone in the last class had a question about the exam coming up. There's an exam after we cover 3.3, which is in about 2 weeks. The exam's in 2 weeks. It goes, I think, from a Thursday to a Monday. It's like the 18th to the 21st or something like that of February. Goes up through 3.3. It will be in the testing center. It's not timed, as long as you give yourself, the time is when the testing center closes. We'll put up some old tests for you to practice from and some review sheet stuff online so you guys can start preparing for that. So, okay. Yes. There's some multiple choice. There's some kind of select all that fit multiple choice, as well as just select one, and then there's some free response. So, good question. Any other questions? Okay. Just want to do some context examples of linearly independent or dependent sets. The first one is color. I claimed yesterday or last time, that red, green, and blue span all of the color spectrum, and you can make any color with red, green, and blue. So if we put in gray and purple into that set, then that's a dependent set, because we can make at least one of these as a combination of the other ones. So you can make gray as a combination of red, green, and blue. You take half a red, half a blue, and half a green, and you get this gray. If you go to the paint, if you go to your like in Microsoft Word, if you go to Paint, like where you get the drawing app, you can go to the color palette, and it won't do it won't do ones to zeros. It'll do 0 to 255. So But I just picked 1 as like the max, 255. So if you did 255 on there and 0, 0, you'd get a red. So purple, you can make this purple with 0.8 of a red and 1 of a blue, and you get that purple. So it's not dependent. If adding a gray or purple in there doesn't help it out, it makes it a dependent set. With just red, blue, and green, that's an independent set. But once we add gray or purple, it's dependent. I could add in gray and take out green, for example, and have red, blue, and gray. That's actually a dependent set. We could actually do row reduction and show that we have all 3 of those would be pivot columns. I could not, however, I could not replace purple. I could not replace green with purple and just do red, blue, and purple. Could someone explain to me why? I mean, I could. I just wouldn't be able to span all colors. Why not? Yeah, go ahead. That's right. The purple doesn't have any green. Blue doesn't have any green. Red doesn't have any green. So there's no way for me to get any greens with those 3. They're still linearly dependent, and I don't have a set that spans all the colors. Right. Yeah. So yeah, that's why it is dependent. It's already a combination of red and blue. Yeah. So it would be equivalent. Replacing green with purple would be the equivalent of just taking green out. That would still be just with red and blue. I can get the places I could get, the colors I could get with just red and blue would be the same I could get with red, blue, and purple. Just with purple in there, I have lots of different combinations to get the same color. So, okay, peanut butter jam bread, peanut butter sandwich, and goober. So here's another list of 5 things. So goober is this stuff. In the same jar, you have jam and peanut butter. There's a nice Studio C skit where this comes in, and Brian Regan also has a skit with this stuff. But with all of these, all 5 of these, this is a dependent set, because with peanut butter jam and bread, I can already get a peanut butter sandwich, and I can already get goober. But I could drop the jam and the bread and just use peanut butter sandwich and goober. And that actually would be an independent set. I could, without jam and bread, I can still get all those other ones. I could get just a bread from peanut butter sandwich and goober, and the way you would get just a bread is you take half a peanut butter and jelly sandwich, peanut butter and jam sandwich, and you subtract half of a goober. And that would give you the equivalent of a slice of bread. So anyway. And in a football game, if you have total offensive yards per game, rushing yards and passing yards, you really only need any 2 of those, and you can get the 3rd. So, right, because rushing yards is, total yards is rushing and passing. Okay. Any questions on that? Yes, John. If we come up after class, and we'll find it on here. Yeah, it's not a negative, it turns out, but yeah, all the values you need are above 0. But yeah, there is a way.
I think people are used to seeing red, yellow, blue as primary colors. So that only works if you're using pigments, but if you're using pixels, if you're adding colors, there's like when I was shooting light out, then those are the 3 states.
Yeah. Yeah, it's easier to think about, yeah, you usually start with a yellow as a primary color, but then you're like, how do you get it with these? And I did look it up last year, and I can't remember what it was. Yes?
So you said that you get anywhere with, on the peanut butter jam sandwich, goober example, you get anywhere with the PB&J sandwich and goober? Is that what you said?
So peanut butter sandwich, goober, and peanut butter.
Oh, okay.
Yeah, so yeah, I'd need at least 3 things, right? Because I have 3, I have kind of 3 values. I have, in each of those, I can have how many breads, how many jams, how many servings of bread, how many servings of jams, and how many servings of peanut butter in there. So I need to have at least 3 in my set to span that space. So is that what you were going to? You thought I only said 2, and you're like, how can that be possible? Yeah, that would be impossible. So, okay. All right, let's turn you loose on the problems of the day. So, yeah, work on 1, 2, and 3 here, and we'll come together as a class in a few minutes.
How are we supposed to write the second one? I can repeat it. Basically, I'm just not sure how I'm supposed to write on number 2, the vectors in the matrix form.
Okay, while Haley's putting something up here, I want to talk about a few things first when we're checking for dependence or independence to see if a set is dependent or independent. There's 3 things you can do first when you glance at a matrix or a set of vectors. The first one is look for if one of the vectors is a 0 vector, then if we've got these 3 vectors here, and you want to know if they were a dependent or independent set, we automatically know it's a dependent set. Why?
Oh, yeah, because if you like set scalar multiples of those equal to another 0 vector, then you can have one of the scalars be non-zero.
Okay, right. Yeah. So so you're using the idea that can we make combinations of these that equal the 0 vector, where the combinations like something times this, something. Didn't leave myself enough room. You're thinking, can I take combinations here and equal the 0 vector where the C1 and C2 and the C3 are not all 0? And yes, we can, because we can take 0 the first, 0 the second, and anything of the third, any non-zero thing of the third, and we get 0. The other definition of linear dependence is, can you make one as a linear combination of the others? And we can make the 0, 0, 0 as a linear combination of these two. I take 0 of this plus 0 of that, and I'll get 0. So either of those arguments tell you that that's dependent. So when we look at problem number 1, we don't have that, so we're going to go back to, so let's look at something else. The other quick thing, are there more vectors than entries in each vector? So not in problem 1, you have 3 columns, you have 3 vectors, and you have 3 entries in each vector. If I added on one more vector, so if I throw down, if I add on one more vector here and look at these columns, I want to know if these columns are now independent or dependent. I don't have to do any work. I automatically know if I'm just worrying about dependent or independent. I already know that these are a dependent set. Why? Go ahead. Okay, someone else? Someone have a hand up over here? Yeah, go ahead. You don't have enough information to solve for a 4th variable. So that's one way to think about it. If I augmented this with something over here, then the most I could solve for x1, x2, and x3, but x4, I don't. It would be a free variable. I don't have enough information. Okay, so that's one way to think about it. Another is, if you don't think about equations, but you think about these as vectors, okay, I'm going to look at the first 2. If this is a linear combination of this one, if there's a scalar multiple, then boom, I'm done. It's dependent. Okay. If this is a linear combination of these, then it's dependent. The best case scenario is all three of these are independent. And if all three of these are independent, then I span R3. And if I span R3, any vector you give me in R3, I can get to as a combination of these, because I can get to any point in R3. So thinking if you have as much information as possible, you'd still only get 3 pivot positions here. You'd only have 3 pivot columns. And since you're in R3, you've spanned the whole thing. So it's dependent. And if you don't have if you only have 2 pivot positions, well, then then these other ones, you even have. Right, yeah, one of the first two is already dependent. So you already know it's dependent there, and you don't have to worry about this last one. So thanks for saving me, Danny. All right. Okay. But and that's not the case in ours. We don't have more vectors than entries in the vector. Is one vector a scalar multiple of the other? So a nice quick thing you can do is start being, oh, is 4, 5, 6 a scalar multiple of 1, 2, 3, or 7, 8, 9? No, because 1 times 4 would give me the 4, but then I'd get an 8. And that's as far as I need to know. So if you check pairwise, none of these are scalar multiples. Second isn't a scalar multiple of the first, third isn't a scalar multiple of the second, third isn't a scalar multiple of the first. Those are all the 3 pairs. If each of the 3 are not scalar multiples, do I know that these are now independent? No. That's not enough. Because the combination to get 7, 8, 9 might be 2 of these and a negative 3 of these to get 7, 8, 9. So that's not enough. If you're looking at rows, like once I get to here, you're like, oh, boom, this row is a scalar multiple of this one. I know it's going to go to 0. I can zero that out. So, okay, but those are 3 ways to quickly tell if if a set of vectors might be dependent. Okay. So the question is, well, once we started row reducing, so this person, Danny, he put this up. He didn't augment it with 0. He just started row reducing. The other strategy over here started with 0. Okay, you can start either way. There's several different ways you can go about doing this. Okay. Danny started to row reduce. Once you get to here, or technically to here, but once you see that you've got a linear, that this is a scalar multiple of this, you know you're only going to have 2 pivot positions. And so there's our 2 pivot positions. And what does that mean? Well, Danny said, oh, since I don't have a pivot position over here, then I should be able to use these 2 to get this 3rd column. So that's what he did. He set these first 2 equal to this 3rd. He did a step between here and here. He divided by a negative 3 to get to 1 and 2. So this would be equivalent if at the very beginning he said, I'm going to see if I can find some combination of 1, 2, 3, and 4, 5, 6 to get 7, 8, 9. And row reduced, and you'd still end up right here. So Danny, why didn't you start like this at the very beginning? Okay, he said he wasn't sure if they were dependent. And you can be in trouble trying to pick one at the very beginning. So for example, so if I've got this set, if I've got this matrix, are these columns independent or dependent? Well, if I tried to test by just picking this 3rd column and seeing if the combinations of the first 2 could equal the 3rd, I'm going to get that there's no solution to that. I already know, actually, there's 0, 0 here, and there's a 1 there. Like this is impossible. But this still is a dependent set. I just chose poorly. If I started row reducing, like I can see that this second column is a scalar multiple of the first column. And if I start row reducing, I'm going to end up with 0, 0, like that. And so this, I don't have a pivot position here. And so this would be the one I'd set over to the right-hand side. And then I can start to see, since this is a like the free variable column, the non-pivot position. Column. That's the one I put over here. That's the one I'm confident I can make with the other ones. So, okay. All right. So Danny kept going, and he finally got to this. And what does this mean? That means that a -1 times the first column. Here, I'm going to rewrite this as a system. So if we started like this, x1, x2 times 4, 5, 6 equals 7, 8, 9. So we're trying to find out, is there an x1 and an x2 that I can put in here and get 7, 8, 9? That's what this system, that's what the system is equivalent to. If you started with this system and row reduced, you'd get to here. So what's x1? x1's a -1. And x2, 2. So that right there tells me, oh, I make this, if I take a -1 of these and 2 of these, then I get 7, 8, 9. Is that the case? Yeah, if I double this, I get 8, 10, 6. Subtract 1 from 8, I get 7. Subtract 2 from 10, I get 8. Subtract 3 from 12, I get 9. So this relationship, this is the linear combination that gets you V3. Okay. Questions about this strategy? Yes, John. Yeah, so you don't have to finish all the way with your reduction, but you do need to go until you find a non-pivot position column, and then you put that over to the right-hand side. Yeah, you can go all the way. You could draw this. You could draw this one later. You could go all the way, but you also might end up with 1, a -1, 0, 0, 2. 1, 0, 0, 0. You might end up with this matrix when you're row reducing. Nope, you won't. Yeah, because you'd make this your entry, and yeah, never mind. Not the case. But you could end up with a matrix like 1, 2, 0, 0, 0, 1, 0, 0, 0. This is your free variable matrix here, right? And that's the one you would put over to the other side in your augmented one. Nice. Okay, other questions? Yes, John.
I'm having trouble conceptualizing something. So theoretically, if the second to last matrix, the 1, 4, 7, and 1, 2, right, is the same as the one next to it, then how is it that 7 times the first vector plus 2 times the second vector is the third vector? Because when we plug in our numbers immediately, the numbers don't add up.
Yeah, so this is because this isn't just this vector. There's this 4 in here too you've got to account for. So that's where the difference is. This is that says x1 plus 4x2 equals 7 and x2 equals 2. So this system is is true, but I haven't gone far enough to know exactly what x1 is. I know that x2 is 2, but I can do back substitution here. But I don't know that I need 7 x1s, right? I need to do some more so I don't have x1. I only have x1 on this side. So yeah, great. So for those online, I forgot to restate that. The question was, like, it doesn't make sense here. If x1 is 7 and x2 is 2, how can 7 of the first column and 2 of the second column also equal the third column? When over here I said a -1 of the first column and 2 of the second column equals the third column. Well, that's not what I'm saying here, because I don't know that I need 7 of the first column yet. I haven't finished solving this. So, okay, good question. Other questions on these before we move over to this one? Okay. Sorry, it's really boring today, guys. So the other strategy, we're going to augment this with 0, 0, 0. The theorem in the book says that these columns or rows will be independent if and only if the solution to the homogeneous system has the trivial solution. So if we solve this and I get 1, 1, 1, I get the 1, 0, 0, 0, 1, 0, 0, 0, 1, and I get all zeros over here. These are always going to be all zeros. But if this has 3 pivot positions, then I'm like, hey, that's the trivial. The only thing that'll work there is the trivial solution. The only way I can get 0 is 0 the first column plus 0 the second column plus 0 the third column. Then I get the 0 vector. But if I don't get ones in all of these pivot positions, then I'm going to have infinitely many solutions here. And then there's an argument we can make about why that doesn't fit, like why we have, why this is not an independent set. So, so we augment it, we start row reducing, we get 0, 0, 0. Here we get, just fix that. Okay, here I get down to the end. The left-hand side, that coefficient matrix looks exactly the same as we got over here. We're just thinking about this differently. So if I think about this as a system, what does this say? Let's translate it back into x1 and x2 and x3. This says x1 minus x3 equals 0. This means the next row, x2 plus 2x3 equals 0. And x3, this is a free variable, right? So x3 equals whatever I want it to be. So I'll let it be t. And so now I'm going to solve for x1 and x2 in terms of x3. So x1 equals x3, which is the same since x3 is t. X1 is t. x2 is going to be a negative 2 x3s, which is the same as a negative 2 t's. x3 is t. So whatever t is going to be what I pick x3 to be, and then I know exactly what x1 and x2 have to be, and it makes this thing true. Let me write that in vector form really fast. x1, x2, x3 equals t times 1, a minus 2, 1. Okay, so there's the vector form of our solution. But now I can rewrite that. I'm going to go back. What does that mean in x1, x2, and x3 from our very beginning system? Well, that means I was looking for an x1 times 1, 2, 3, plus an x2 times 4, 5, 6, plus an x3 times 7, 8, 9. That equals 0, 0, 0. And I found one. I actually found infinitely many. But let me just pick the easy one. I'm going to let t equal 1. So then x1 equals 1, x2 equals a negative 2, x3 equals 1. So I'm going to just substitute those in. x1 is 1, x2 is negative 2, right? X3 is 1. Now, I've done enough talking. It's your guys' job. Okay? Tell me what you can do with this to give me a dependence relationship. How can I use this to find out what combination of two of these can I use to get another one? So talk to your neighbor about this.
Best I got is maybe just do like a system of equation or something, but I don't know how that's really different than just doing the augmented row matrix, but that's the only thing that I got.
Okay, let's come back. So I heard some people say, well, we can solve for 7, 8, 9. This is an equation. Let's just solve for 7, 8, 9 and see what it is, see what it equals. So 7, 8, 9, I'm going to take the 1, 2, 3 over. So I'm going to subtract 1, 1, 2, 3s. And I'm going to add 2, 4, 5, 6s to get this relationship. Now I know that I need a -1 of column 1. I'm going to call it V1 because we've been using C1 to be column constants. But -1 times V1 plus 2 times V2, and that equals V3. So that's one way to show that these are dependent, because I found a dependent relationship. I know how to get V3 with combinations of these other vectors. And that is the exact same thing we found over here. Okay. This way you can also see I could solve for vector 2 in terms of vector 1 and vector 3. Or I could solve for vector 1 in terms of vector 2 and vector 3. You can't always do that, because if we had another vector here that had to be 0, had to be zeroed out, or I'll just use this first one as an example. If this coefficient here was 0, then I could solve for vector 2 in terms of vector 3, and I could solve for vector 3 in terms of vector 2, but I can't solve for vector 1 in terms of vector 2 and vector 3, because it's got a 0 coefficient. It's not there. Or I'd have to divide by 0, which makes the world explode. So it's like Thanos snapping his fingers or something. I don't know. Thanos, did I get that right? I haven't watched those, so I don't know. Okay. I just pick things up for my kids talking. So okay, questions about this strategy? Okay. Yes.
Does this only work when we know which one is like the bigger one in the combination of the two, I guess?
When you know which one is the bigger one? What do you mean by the bigger one?
7, 8, 9 is a combination of the other two vectors. If we didn't know which one was the combination, could we use that method up there?
Oh, so that question was, if we didn't know which one was the combination, could we use this method? Yes, you still could, because no matter what, if you get a free variable, then it's going to be a dependent set. And when you solve and put it into this like vector form, so put it into equations, you're going to have a free variable. You can put it into this vector form. You can use these to create this equation. And then you can find out whatever relationships you want. So yeah, even if it was the second one, it would just be that x2, we'd solve x1 and x3 in terms of x2. And so we'd still have some constants over here. X2 would be 1. Like that one would probably be 1. And one of these might be 0. That's okay. Both of them will not be 0. If both of them are 0, then x2 means it's a pivot position. So did that help? Yeah. Okay, other questions? Okay, we're going to do it one more way. A third way. This way is going to be familiar, more familiar, and a little bit crazier. I just have to do something crazy to make you think I'm not so square, because I don't watch whatever those movies are. Yeah. The other strategy, I have the strategies listed here. The other strategy is this one. The 1 and 2 were basically the ones we already showed. But convert the column vectors to row vectors. And so we're going to make a row matrix instead of a column matrix. And then row reduce, and we have to keep track of all the steps. Because as we do row reduction, we're finding combinations of some rows. And if we have a 0 row at the bottom, then we can backtrack to find out what combination of rows we used to equal that bottom row. So that's how we're going to find the dependency relationship. So instead of starting with column 1, 2, 3, column 4, 5, 6, and column 7, 8, 9, I'm going to start with row 1, 2, 3. Oops. Yeah, 4, 5, 6, 7, 8, 9. You don't even have to augment it with 0 here. Okay, so we're going to do row reduction. We're going to keep track of our moves. I can take a -4 times row 1 plus row 2, and I get, oops, it's going to be my new one down here. A -4 times row 1 plus row 2, and that's going to be 4, 5, 6. Okay, 0, a -3, -6, right? Because yeah, 3 times 4 is -12, plus a 6 is that. Okay, and now I'm going to do a -7 times row 1 and add it to row 3. -7 row 1 plus row 3, and I get 0. Here I get 14. -14 plus 8 is a -6. -21 plus 9 is a -12. Okay, and I see that I'm going to have a row of zeros here. How do I make that row of zeros? So I'm going to use the same notation that the book uses, and it calls this new row to row 2 prime, and it calls this new row 3 prime. And if I multiply this row 2 prime, if I multiply that by a -2 and add, I get 0, 0, 0. So a -2 times row 2 prime plus row 3 prime equals 0, 0, 0. And we can call that row 3 double prime if we wanted to. Luckily, this isn't too bad. But how's this helping me? Well, if I'm doing row operations and I got this row of zeros, that means some combination of these first 2 rows I was able to use to cancel out that whole row. So some combination of these has to equal that last row. And I can recover that with these operations that I did. So row 3 double prime is the 0 vector. Okay? And that 0 vector is the same as, how did I get that? That's the same as a -2 row prime 2 plus row 3 prime. But that's the same as what's row 1, or row 2 prime is this one. So a -2 times a -4 row 1 plus row 2 plus, and what was row 3 prime? That's this one. That's a -7 times row 1 plus row 3. And that whole thing is 0. That whole thing is the 0 vector. Now I can solve, I know row 3 double prime, I know like this row 3 at the beginning, somehow I can use these two to equal this row. And how do I find that? I just solve for row 3 right here. This row 3 was my beginning row 3, right? So here's row 3, here's row 2, here's row 1. And if I distribute this out and solve, I keep R3 on one side and solve, what do I get? I get, that's +8 row 1 -2 row 2 -7 row 1. So my 8 and my -7 will make it so I have 1 row 1. If I pull that to this side, I get a minus row 1. I had a -2 row 2s. Let's pull it to this side, -2 row 2s. And what do I have left? Row 3. And that's the exact same relationship that we found this way, and the exact same relationship we found over here. That a -1 of the first plus the second plus 2 times the second equals the third. Let's did it with rows this time instead of columns. Okay, questions? Yes?
So with that last row vector thing over there with row 3 double prime, couldn't you also just rewrite that as a regular matrix with the column, like the row of zeros or the column of zeros on the right and solve for it?
What do you mean, rewriting this way? Just transpose this whole thing?
Yeah, you get 1, 2, 3, 0, -3, -6.
So where would you go from here?
Or it would be 0, then -3, then -6. Because those symbolize the vectors you put in the first place.
Right.
I just wondering if it would work.
Yeah, why don't you come up and talk to me? We're out of time, so yeah. Thanks, everybody.